Welcome to these gentle, soothing stories for sleep. I am so glad you are here. Whether you are preparing to drift off to sleep, relaxing after a long day, or simply seeking a quiet companion, you have come to the right place. Tonight, we will begin a journey into the heart of the universe's greatest and most gentle mystery, a story of an invisible presence that shapes our cosmos in the most profound ways imaginable. Before we begin, I would love to know where you are listening from tonight, or perhaps how your day was. Please feel free to leave a comment below. Wherever you are in the world, I hope you are feeling comfortable, safe, and ready to explore something truly extraordinary. And if you find these soothing scientific journeys a pleasant and restful companion, please consider liking this video and subscribing to the channel. It helps more souls who are searching for this kind of peace find their way here. Now, let us begin. Imagine, if you will, a carousel at twilight, just as the sun has dipped below the horizon, leaving the sky in shades of deep violet and soft rose. The first stars are beginning to emerge, faint and shy, and down here on the ground, the warm, golden lights of the carousel have just blinked on. You can hear the gentle, looping melody of the organ music, a sound that feels like a memory even if you are hearing it for the first time. The carousel begins to turn, slowly at first, and then it picks up speed, the painted horses with their jeweled bridles rising and falling in a steady, graceful rhythm. The lights blur into glowing circles, painting streaks of gold against the deepening blue of the evening. If you were riding on one of the outermost horses, you would feel a gentle but insistent pull, a force that seems to want to fling you outwards into the quiet park. But you are held in place, anchored to the spinning machine, a part of its beautiful, predictable dance. You know, without having to think about it, that the horses near the bright, shining center are moving in smaller circles, and that you, out here on the edge, are traveling the farthest and the fastest. Or are you? In our familiar world, on a solid, spinning disc, like a carousel or a record on a turntable, the farther you move from the center, the faster you must travel to keep up. But in the cosmos, things work a little differently, governed by a force far more ancient and elegant than gears and motors, the force of gravity. Let us now zoom out from this little carousel in the park, pulling away from the soft grass and the quiet evening sounds. We rise above the town, above the clouds, until the earth itself is a beautiful blue and white marble below. We are drifting now in the silent, velvet blackness of space, and before us is a sight of almost unimaginable grandeur, a spiral galaxy. It looks, from this impossible distance, just like our carousel, a vast, glittering pinwheel of light, turning slowly against the darkness. It is made of hundreds of billions of stars, each one a sun, and they are all held in a delicate cosmic dance by the invisible hand of gravity, emanating from the supermassive glowing core at the galaxy's center. For centuries, we believed we understood this dance perfectly. An astronomer named Johannes Kepler, long ago, figured out the basic rules for our own solar system. He showed that the planets closest to the sun, like Mercury, race along in their orbits, while the planets farther out, like Neptune, travel at a much more stately and leisurely pace. It makes perfect sense. The pull of gravity is strongest near the massive center and grows weaker the farther away you go. Therefore, objects on the edge should be moving the slowest, or else the weak gravitational pull would not be enough to hold them, and they would be flung off into the lonely darkness of intergalactic space. For a very long time, we assumed that galaxies must work the same way. The great, brilliant concentration of stars and gas at the center holds the most mass, and therefore the gravity should be strongest there. The stars on the very edge of the pinwheel, far from that central glow, should be moving slowly, tracing their immense orbits with a calm, celestial patience. In the 1970s, an astronomer named Vera Rubin, a woman of incredible patience and insight, decided to test this assumption. She spent countless nights in the quiet of a mountain observatory, pointing a telescope at our neighboring galaxies and carefully measuring the speed of the stars. She measured the stars in the bright, bustling center, and then she measured the faint, lonely stars at the very edges of the visible disk. And what she found was impossible. It was as if she were watching a carousel and noticed that the horse on the absolute outer edge was moving at the exact same speed as the one closest to the center. The stars at the galactic rim were moving far, far too fast. So fast, in fact, that the gravity from all the visible stars, all the shining gas, and all the glowing dust in the galaxy combined was not nearly strong enough to hold them in their orbits. The galaxy was spinning itself into pieces, except it wasn't. It was stable, serene, and whole. The beautiful cosmic carousel was turning with impossible speed, yet none of the horses were flying off. This quiet, revolutionary observation was a whisper that has since become the loudest question in all of cosmology. The universe was not behaving as it should. It was holding a secret, a vast and invisible secret. The stars are moving too fast, yet the galaxy does not fly apart. Something invisible must be holding it all together, a silent, unseen hand guiding the cosmic dance. What if the empty space around you was not truly empty? What if the silent, dark voids between the stars and even the seemingly vacant space in this very room were filled with a substance so profoundly different from our own that it passes through the walls, through your body, and through the very planet beneath us, as if they were not even there? This is the strange and beautiful implication of Vera Rubin's discovery. There must be more to the universe than meets the eye, vastly more. To understand the sheer scale of this mystery, imagine yourself waking up on a cool morning, looking out the window into a world blanketed by a thick, heavy fog. You cannot see the trees at the end of the garden, nor the house across the street. You can only make out the vague, soft shapes of the things nearest to you. The world feels muffled, gentle, and filled with an unseen presence. You know, logically, that the world is still out there, complete and whole within the mist. But your senses tell you a different story, one of an incomplete and ghostly landscape. This is precisely the situation astronomers find themselves in when they look out into the cosmos. They are peering through a kind of cosmic fog, not of water vapor, but of something far more mysterious. They are seeing only the faint lights, while the true substance of the universe remains shrouded. The science behind this is both simple and profound. We have two ways to weigh a galaxy. The first method is the most straightforward. We can count what we can see. We look at the galaxy's light, we count the number of stars, we estimate their size and mass, we measure the amount of glowing gas and dust, and we add it all up. This gives us what we call the luminous mass, the mass of all the things in the galaxy that shine, that interact with light. The second method is the one Vera Rubin used. We can measure how the galaxy moves. The fundamental principle of the universe, as laid down by Isaac Newton and later refined by Albert Einstein, is that mass creates gravity, and gravity dictates motion. By measuring how fast the stars in a galaxy are orbiting, we can calculate the total amount of gravity needed to hold them in place. And since we know that gravity comes from mass, this tells us the galaxy's true weight, its gravitational mass. Herein lies the impossible problem. When we weigh a galaxy by counting its stars, and then we weigh that same galaxy by measuring its spin, the numbers do not match. They are not even close. The gravitational mass of a galaxy is immensely, staggeringly larger than its luminous mass. It is like seeing a single, small lantern lit on the deck of a ship sailing on a dark ocean at night. Based on that one tiny light, you might guess you are looking at a small fishing boat. But then, you notice the colossal wake. The vessel is leaving behind, the way the water is being churned and displaced on a massive scale. The motion of the water tells you that you are not looking at a fishing boat at all, but at a gigantic, unseen supertanker. Its vast, dark hull submerged invisibly in the nighttime sea. The single lantern is the only part you can see, but the ship's true nature, its immense mass, is revealed only by its effect on the world around it. The stars and gas we see in a galaxy are just that single lantern. The galaxy's spin, its gravitational footprint, reveals the presence of the invisible hull. This vast quantity of missing mass, this unseen anchor holding the stars in their impossibly fast orbits, was given a simple, yet deeply mysterious name: dark matter. It is dark because it does not emit, reflect, or interact with light in any way. And it is matter because it has mass, and therefore it has gravity. The calculations suggest that for every 1 kilogram of the familiar, visible matter that makes up you, me, the planets, and the stars, the universe contains roughly 5 kilograms of this strange, invisible substance. 85% of all the matter in the cosmos is a ghost. This realization is a profound lesson in humility. For nearly all of human history, we have trusted our eyes to reveal the nature of reality. We have built our understanding of the world upon the light that we can see. But the universe is gently telling us that our senses, as wonderful as they are only tuned to a tiny fraction of what is real. The most significant component of the cosmos is completely invisible to us. It forces us to ask a deeply philosophical question. What does it mean to exist if you cannot be seen, if you leave no trace in the light? Dark matter does not care about our definition of existence. It is there, its gravitational presence shaping the cosmos on the grandest of scales, forming a silent, invisible skeleton upon which the shining universe we know is built. This unseen anchor does not just hold individual galaxies together, keeping them from flying apart. Its influence is felt on a scale so vast that it bends the very fabric of space-time, warping and distorting the light from the most distant corners of creation as it travels across the eons to reach us. Have you ever looked through the curved base of an old, hand-blown wine glass and seen how the world behind it seems to warp and swim? A candle flame on the other side of the glass might appear to stretch into a gentle arc of light, or even split into 2 or 3 flickering images. The glass itself is clear. You can see right through it, but its very substance, its elegant curvature, has a profound effect on the light that passes through. The light, traveling in its perfectly straight lines, is forced to take a detour, to bend its path as it navigates the invisible contours of the glass. The image of the world is altered, not because something has blocked the light, but because the medium it traveled through has sculpted its journey. This simple, beautiful effect, one we can hold in our hands, is a perfect miniature of one of the most powerful pieces of evidence we have for the existence of dark matter. It is a phenomenon that allows us to see the shape of the invisible, written in a language of bent starlight. To feel this a little more deeply, imagine standing beside a perfectly clear, shallow stream on a sunny day. The water flows gently over a bed of smooth-coloured stones. You can see a particularly beautiful, dark grey pebble resting on the bottom. As the water ripples and flows over it, the image of the pebble seems to shimmer and dance, its shape momentarily wavering and distorting. You are not seeing the water itself, for it is as clear as air, but you are seeing the undeniable effect of the water on the light travelling from the pebble to your eyes. The river of water is bending the river of light. Now, let us trade this gentle stream for the vast, cosmic rivers of space-time. The great insight of Albert Einstein was that space and time are not just an empty, static backdrop for the universe. Instead, they are a dynamic, flexible fabric, a 4-dimensional landscape, and this landscape is shaped by the presence of mass and energy. His theory of general relativity is often described with a simple analogy. Imagine a large, taut rubber sheet. If you place a heavy bowling ball in the center, the sheet will sag and curve around it. This curvature is a representation of how massive objects warp the fabric of space-time. Now, if you roll a small marble across the sheet, it will not travel in a straight line. It will follow the curve created by the bowling ball, its path bent by the warped geometry of the sheet. Light, for all its incredible speed, is no different. As it travels across the universe from distant galaxies, it too must follow the contours of space-time. When this light passes by a very massive object, like an entire cluster of galaxies, its path is bent, just like the path of the marble on the rubber sheet. This effect is called gravitational lensing. The immense gravity of the galaxy cluster acts like a cosmic telescope lens, bending and sometimes even magnifying the light from whatever lies behind it. For astronomers, this is a wondrous gift. It allows them to see galaxies that are so far away they would otherwise be too faint to detect. We can point our telescopes at a massive cluster and see the light from even more distant galaxies behind it. Their images stretched into beautiful, ghostly arcs and rings of light, smeared around the central cluster. It is one of the most stunningly beautiful sights in the night sky, a direct visual confirmation of Einstein's theory. But it is also the scene of a profound cosmic crime. When we calculate the amount of mass needed to create the spectacular lensing we observe, we run into the same familiar problem. We add up all the mass from the hundreds or even thousands of galaxies we can see in the cluster. We add the mass of all the superheated gas that surrounds them, and the total mass is not nearly enough. The warping of space-time is far too extreme. The cosmic lens is far too powerful. To create the gravitational distortion we so clearly see, there must be 5 to 6 times more mass than we can account for. The bowling ball creating the dip in the rubber sheet is, for the most part, completely invisible. The galaxy cluster is anchored by a colossal, transparent cloud of dark matter, and it is this unseen mass that is truly bending the river of light. We are not seeing the dark matter itself. We are seeing its shadow, cast not in darkness, but in distorted starlight that has travelled for billions of years to bring us the message. The universe is showing us a magic trick. It is revealing the shape and location of the invisible by the way it sculpts the visible. And this evidence, written in the very geometry of the cosmos, tells us that this unseen anchor is not just a strange quirk of individual galaxies. It is a fundamental, dominant component of the largest structures in the universe. We have seen its effects on galaxies, keeping them from flying apart, and now we have seen its effects on light itself, guiding its path across the eons. These observations are like seeing fresh footprints in newly fallen snow. They are undeniable proof of a presence, even if we cannot see who or what made them. But what about the story of the universe's very beginning? Was it there, even then, in the cosmic dawn? Imagine finding an old vinyl record in a dusty attic, a recording of a sound that has not been heard for a very long time. You place it gently on the turntable, lower the needle, and a sound emerges from the speakers. It is not a clear melody or a voice, but a soft, gentle hiss, a uniform and persistent crackle that seems to fill the room. This faint hiss and pop is not the music itself, but it is the texture of the medium, the sound of time itself embedded in the grooves. In a way, this is what it is like for astronomers when they listen to the deepest and most ancient sound in the universe. It is a sound that has been travelling for over 13.8 billion years to reach us, an echo from the very dawn of time. This sound is not made of vibrations in the air, but of faint, cold light, a whisper of microwaves that comes from every direction in the sky, with almost perfect uniformity. It is called the cosmic microwave background, or the CMB, and it is the most precious artifact in our cosmic museum. This ancient light is the afterglow of the Big Bang. In its infancy, the universe was an incredibly hot, dense, and opaque soup of particles and energy. Light was trapped within this primordial fog, unable to travel freely. But as the universe expanded and cooled, a magical moment occurred, about 380,000 years after the beginning. The cosmos became transparent. The light that was trapped was suddenly set free, and it has been traveling through the expanding universe ever since, growing cooler and fainter, eventually becoming the gentle wash of microwaves we detect today. The CMB is nothing less than a baby picture of our universe. It is a snapshot of what the cosmos looked like in its absolute infancy. And when we look at this picture, we see a miracle. It is a picture of almost perfect uniformity. The temperature of this background light is the same everywhere we look, to an astonishing degree of precision. But it is not absolutely perfect. Sprinkled throughout this ancient light are tiny, minuscule fluctuations in temperature, ripples on the surface of a near perfectly still pond. Some spots are 100,000th of a degree warmer, some 100,000th of a degree cooler. These tiny ripples might seem insignificant, but they are the most important features in the entire cosmos. They were the seeds of everything we see today. The slightly denser, slightly cooler spots were the places where gravity had a slightly stronger grip. Over billions of years, these seeds were destined to grow, pulling in more and more matter to eventually form the first stars, the first galaxies, and the vast clusters of galaxies that populate our universe. Here, however, we encounter another impossible problem. a deep paradox that lies at the heart of our own existence. When we use our laws of physics and run computer simulations, we start with those tiny seeds we see in the baby picture of the universe. We add all the ordinary matter, the hydrogen and helium that were created in the Big Bang, and we let gravity do its work over 13.8 billion years. And the simulation fails. It fails spectacularly. The force of gravity from ordinary matter alone is far too weak. It could not have gathered that primordial gas quickly enough. In the time available, it could not have grown those minuscule seeds into the vast and majestic cosmic structures we see around us today. The universe we live in should not exist. The only way the simulation works, the only way to build a virtual universe that looks like our own, is if we add a crucial, invisible ingredient. We have to assume that the universe was filled, from the very beginning, with a vast amount of dark matter. This dark matter did not interact with the light, so it could begin to clump together gravitationally long before ordinary matter could. It created a hidden, invisible scaffolding throughout the early cosmos. When the universe finally became transparent and the ordinary matter was set free, it found these pre-existing gravity wells, these deep pools of invisible mass, already waiting for it. The gas then simply fell into these dark matter halos, which acted as cosmic nurseries, kick-starting the process of galaxy formation and giving it the immense gravitational boost it needed. We are listening to the echoes of creation. And within that echo is the clear signature of something that was present from the very first moments. A silent architect that laid the foundations of the cosmos and sculpted the universe we inhabit long before the very first star ever ignited its fires. If this invisible architect has been with us since the beginning, shaping the universe at every stage of its life, then what is it actually made of? The search for its true identity is a journey that will take us from the grandest scales of the cosmos to the deepest, quietest, and most silent places on our own Earth. Can you imagine a particle, a single mote of existence, that can pass through your entire body from head to toe without disturbing a single atom? A particle that could journey from the surface of the Earth, through the soil, through the rock, through the molten iron core, and out the other side into space, without ever once colliding with anything, as if the solid planet itself were nothing more than an empty ghost. This is the profound strangeness we must contemplate when we ask what dark matter might be. We have traced its gravitational shadow across the cosmos, but to understand its substance, we must now journey into the realm of the infinitesimally small, into the world of particle physics. It is a world governed by rules so counterintuitive and beautiful that they can feel like a form of magic, a world where the most fundamental components of our reality reveal their true, ethereal nature. To appreciate just how different dark matter must be, let us first consider the substance of ourselves. Imagine for a moment being inside a vast, empty cathedral. The air is cool and still, and the light from the stained glass windows paints long, silent columns of color through the space. Your footsteps echo from the stone floor, the sound traveling outwards until it is swallowed by the immense, quiet emptiness. The very space itself feels serene and untouchable. This is the world, as a dark matter particle might experience it all the time. A world of vast open spaces between the tiny nuclei of atoms. But for us, the world is solid. If you reach out and press your hand against one of the cold stone pillars of the cathedral, it feels undeniably real. Your hand does not pass through it. This feeling of solidity, the very act of touch, is not what it seems. Your hand is not truly, physically, making contact with the pillar. Rather, the tiny electrons in the atoms of your hand are powerfully repelling the electrons in the atoms of the stone, thanks to a fundamental force of nature called the electromagnetic force. This is the force that governs light, electricity, and magnetism, and it is what makes the world feel solid and tangible to us. It is the force that allows us to bump into things. Our entire understanding of the building blocks of the universe is collected in what we call the standard model of particle physics. It is a beautiful and elegant theory, a kind of cosmic cast of characters, containing the familiar protons, neutrons, and electrons that build our atoms, as well as more exotic particles like quarks, neutrinos, and bosons. All of these particles, the entire zoo of matter that we know and understand, constantly interact with each other through a few fundamental forces, especially that electromagnetic force. They are constantly talking to each other, bumping into each other, and exchanging light. But dark matter, whatever it is, must be an outsider. It does not belong to this club. We know this because it is dark. It does not emit, absorb, or reflect light, which means it must not feel the electromagnetic force. It is a ghost in the cosmic machine, a particle that is immune to the very force that makes our world solid and visible. This is why it can pass through the Earth as if it were not there. This simple, powerful fact leads us to the most popular and compelling candidate for what dark matter might be. Physicists have given it a wonderfully evocative name, a WIMP, which stands for Weakly Interacting Massive Particle. Let's break that name down, for it tells us everything we need to know. First, it is massive. This is essential. The particle must have some heft to it, because we know dark matter exerts a powerful gravitational pull. There has to be a lot of mass in these invisible halos to hold the galaxies together. Second, it is weakly interacting. This is the key to its ghostly nature. It does not feel the electromagnetic force, nor the strong nuclear force that binds atoms together. The theory suggests it only interacts with our world through two means: the gentle, long-range touch of gravity, and possibly the weak nuclear force, a force so feeble and short-ranged it is primarily responsible for certain types of radioactive decay. Its ability to interact is so incredibly low that a WIMP could fly through trillions of kilometers of solid lead before it would be expected to hit anything. It is the ultimate introvert of the subatomic world. This idea leads us to a profound thought about the nature of reality. We are made of interactive, social, bumping into each other stuff. Our entire experience is defined by these interactions, by the feeling of the sun on our skin, the taste of food, the sight of a loved one's face. But the universe is telling us that the majority of its substance, the true scaffolding of the cosmos, is aloof, serene, and almost completely non-interactive. It passes through us at every moment, a silent, ghostly river, completely unaware of our solid, tangible, and light-filled world. Our reality is just one way of being, perhaps even a rare and special way of being, in a universe that is mostly silent and dark. But if this is true, if we are swimming in a constant sea of these ghost particles, then it poses the next great question, a challenge of almost impossible difficulty. How, then, do you catch a ghost? How do you build a trap for a particle that feels nothing and touches almost nothing? To find the universe's greatest and most elusive secret, we must embark on a journey that feels profoundly counterintuitive. We must travel not up into the starry sky, but deep, deep down into the warm, silent darkness of the earth. We must leave the world of light and air behind us and descend into an ancient realm of rock and pressure. The search for a particle from the heavens requires that we build the quietest places on the planet, sanctuaries of stillness buried beneath mountains. Imagine stepping into the metal cage of a mine elevator. The heavy gate slides shut, and with a gentle jolt, you begin your descent. The daylight of the surface world shrinks to a small, bright square above you, and then it is gone. You are enveloped in a cool, mechanical darkness. The only sound the hum of the winch and the rattle of the cage against the guide rails. The air grows cooler and takes on the faint, clean scent of damp stone. As you descend deeper and deeper, a profound feeling of quiet begins to settle in. The noise of the surface world, the wind, the birds, the distant traffic is completely gone, absorbed by the immense weight of the rock above you. Down here, a kilometer or more beneath the ground, there is a silence that feels ancient and absolute. The rock itself acts as a protective blanket, and it is within this deep terrestrial stillness that humanity listens for the faintest whispers from the cosmos. The reason for this journey into the depths is a simple one. Our planet's surface is an incredibly noisy place. It is constantly being bombarded by a storm of high-energy particles from space known as cosmic rays. Every second, particles born in the sun or in distant, exploding stars are raining down upon us, creating a shower of secondary particles that pass through our bodies and our laboratories. This constant particle static would make it completely impossible to listen for the extraordinarily rare and subtle signal we are hoping to find. To hear the whisper-faint sound of a single dark matter particle, scientists must go to the quietest places imaginable, and the best way to do that is to put a few kilometers of solid rock between their experiment and the sky. This immense layer of stone acts as a natural shield, filtering out the cosmic ray noise and leaving a pristine, silent environment, perfect for listening. And so, in former gold mines in South Dakota, in nickel mines in Canada, and in tunnels dug deep beneath Italian mountains, physicists have built some of the most extraordinary experiments ever conceived. In vast, clean-room caverns, they have assembled detectors of breathtaking sensitivity and purity. These are the traps we have built to catch a ghost. One of the leading designs involves a large tank, like a polished metal vat, filled with an incredibly pure, liquid form of an element called xenon. This liquid xenon is cooled to a temperature far below freezing, and it is surrounded by an array of extremely sensitive light detectors. The entire apparatus is shielded by layers of lead and water, all designed to stop any stray local radiation. Then, the scientists wait. They wait in the profound silence of the deep earth for a single, rare event. The theory is that as billions upon billions of WIMPs stream harmlessly through the earth, through the laboratory, and through the detector itself, just once in a great while, a single WIMP will, by a sheer fluke of probability, fly too close to the nucleus of a single xenon atom and collide with it directly. This collision would be unimaginably gentle, but it would cause the xenon nucleus to recoil, like one billiard ball striking another, and in the process, it would release a tiny, almost imperceptible flash of light and a few free electrons. This minuscule spark, this single ping in the immense cold silence, is the signal they are looking for. It would be the first direct evidence of the invisible world that surrounds us. There is a beautiful and profound poetry in this endeavor. To understand the grandest structures in the heavens, we burrow deep into the body of the earth. To find the most ethereal and non-interactive substance in the universe, we build the quietest, most still, and most carefully shielded environments ever created by human hands. We surround our jeweled detectors, our vats of pure liquid xenon, and our crystals of perfect germanium, with a monastic-like devotion to silence, hoping to hear a single message from the dark. But for decades now, we have been listening, and the minds have remained quiet. The detectors, despite their ever-increasing sensitivity, have heard nothing. This great silence is beginning to trouble us, forcing us to wonder if we are searching for the right thing. But what if dark matter is not a heavy, shy particle like a WIMP? What if it is something stranger still, something far lighter than a feather, something born not as a particle, but as a vast, whispering field that fills all of space? Have you ever sat in a perfectly quiet room, late at night, and felt a faint hum? It is a vibration so subtle you are not even sure if you are truly hearing it, or just imagining it. It is a feeling more than a sound, a low-frequency energy that seems to exist at the very edge of your perception, a baseline thrumming that underlies the silence. This experience of sensing a vast, pervasive, yet barely detectable field of energy might be closer to the true nature of dark matter than the idea of a single, lonely particle colliding with an atom in a mine. The great silence from our underground detectors has encouraged us to think in new ways, to imagine a possibility that is in some ways even stranger and more profound. That dark matter may not be a particle at all, but a vast, whispering field that permeates every corner of the universe. To grasp this idea, imagine standing on a gentle hill overlooking a wide, expansive field of tall, golden grass. A steady breeze is blowing. You cannot see the wind itself. The air is perfectly transparent, but you have no doubt that the wind is there. You see its presence written in the beautiful flowing patterns it creates, the waves and ripples that travel across the entire sea of grass. The whole landscape is alive with the motion of an invisible force. You feel it on your skin. You see its influence on everything around you. This is a beautiful analogy for the second major candidate for dark matter, a particle called the axion. Unlike the WIMP, which we imagine as a discrete, heavy particle, like a single invisible cannonball flying through space, The axion is theorized to be an incredibly, almost unbelievably light particle. It is so light and so abundant that it does not behave like an individual particle at all, but rather like a coherent, slow-moving wave, a vast and gentle quantum field that fills all of space. If WIMPs are the lonely raindrops in a cosmic storm, the axion field is like the slow, inexorable, rising tide of the ocean itself. We are swimming through it at every moment. It is the hum beneath the silence. This different conception of dark matter requires a completely different method of searching. You would not try to catch the wind in a jar to prove its existence. You would build a windmill to feel its collective force. In the same way, experiments designed to find the axion are not looking for a single collision. Instead, they are trying to harness the collective, wave-like nature of the entire field. At the University of Washington, an experiment called the Axion Dark Matter experiment, or ADMX, is doing just that. Inside a powerful superconducting magnet, cooled to temperatures colder than deep space, is a precisely tuned resonant cavity, which is essentially a hollow copper can. The theory suggests that in the presence of a very strong magnetic field, an axion from the great cosmic field can, very rarely, be converted into a single particle of light, a photon. The resonant cavity is designed to amplify this specific conversion, to make it ring like a perfectly cast bell. Scientists are, in essence, trying to ring the silent cosmic field, listening for the clear, pure note of a single photon being born. They sweep the tuning of their cavity very slowly, like turning the dial on an old radio, listening for a faint signal amidst the cosmic static. This beautiful idea completely shifts our perspective on the nature of the mystery. Is dark matter a collection of individual, separate things, a swarm of ghost particles passing through us? Or is it a fundamental and continuous property of space itself, a gentle, unseen energy that we are immersed in at every moment of our lives, like a fish is immersed in the water of the sea? This possibility is in some ways more intimate. It suggests that dark matter is not just a visitor passing through our world, but a part of the very fabric of our world, a silent, vibrating backdrop to all of existence. The search for the axion is the search for the fundamental tone of this silent universe, the baseline hum of the cosmic song. We have considered the very heavy and the very shy particle, the WIMP, and now we have considered the very light and wave-like field, the axion. But there is a third, more ancient and perhaps more haunting possibility, a candidate for dark matter that is not a new type of particle at all, but is instead made of the ghosts of a time before the first stars were ever born. Imagine a black hole, not one of the giants we read about, born from the spectacular death of a massive, collapsing star. Imagine instead a black hole forged in the unimaginable furnace of the first second of the universe's existence. A phantom of creation itself, wandering the cosmos silently for 13 billion years, its presence betrayed only by the subtle way it bends the space and time around it. This is the third great possibility for the identity of dark matter, an idea that is both deeply compelling and strangely unsettling. It suggests the darkness is filled not with exotic, new particles, but with a population of ancient, invisible ghosts made of matter we already know, matter that has been compressed into a state of perfect and eternal darkness. To feel the unnerving essence of this idea, picture yourself standing at the edge of a very old, deep well, carved from dark stone. You lean over the edge and look down. There is no reflection of your face, no glint of light from the bottom, just an unnerving, absolute blackness that seems to absorb the sunlight and your gaze along with it. There is a profound sense of one-way passage, a feeling of pure absorption that is a miniature, terrestrial version of the feeling a black hole evokes. It is a place where things go in, but nothing ever comes out. Normally, these cosmic wells are created only when the most massive stars in the universe, many times larger than our sun, finally run out of fuel. In their final moments, their own immense gravity overwhelms them, and they collapse catastrophically, crushing themselves down into an infinitely dense point from which not even light can escape. But what if there was another way to make a black hole? The theory of primordial black holes, or PBHs, suggests that there was In the very first moments after the Big Bang, the universe was not the calm, orderly place we see today. It was a chaotic, turbulent, and unimaginably dense soup of energy. The theory goes that in this violent environment, some regions might have, just by chance, become so incredibly dense that they spontaneously collapsed under their own gravity, punching a hole in the fabric of space-time without ever having been a star. These primordial black holes would not be like their stellar cousins. They could have been created in a vast range of sizes, some as massive as thousands of suns, and others far, far smaller, perhaps no bigger than a mountain, or a grain of sand, or even a single atom, each one still containing the compressed mass of a great asteroid or a moon. A vast, swarming population of these ancient, wandering black holes, forged in the fires of creation, could easily account for all the missing mass we attribute to dark matter. They would be made of ordinary stuff, but compressed into an invisible, non-interactive, and perfectly dark form. Finding these primordial phantoms is an immense challenge. They are completely dark, and unless they are actively swallowing matter, they are utterly silent. So we must look for them indirectly, using the universe as our detector. One method is to watch millions of distant stars, looking for rare and fleeting gravitational lensing events. If one of these wandering black holes were to pass directly between us and a distant star, its gravity would act as a tiny lens, briefly and characteristically brightening the starlight for a few moments, an effect called microlensing. Searches for these events have been conducted, but they have not found nearly enough to account for all of the dark matter. Another, more remote possibility is that these black holes are not perfectly black. The physicist Stephen Hawking predicted that black holes should, over immense timescales, very slowly evaporate, leaking a faint whisper of energy known as Hawking radiation. For very small primordial black holes, this faint glow might just be detectable as a background of strange gamma rays. So far, we have found no such signal. This is perhaps the most existentially unsettling of all the possibilities for dark matter. That the invisible substance holding our galaxy together is not a gentle sea of new particles, but a cold, vast population of invisible, primordial predators that have been roaming the cosmic dark since the beginning of time. It would mean that the universe is filled with countless points of no return, ancient relics of its own violent birth. With all of these fantastical candidates on the table, the shy, heavy ghosts, the whispering, lightweight fields, and now these primordial phantoms, we are faced with a deepening puzzle. Our theories are beautiful, our traps are ingenious, and yet the universe remains silent, offering no definitive clues. This profound lack of discovery, this continued quiet from the cosmos, forces us to look not only at our candidates, but at the very nature of our search and the psychology of what it means to seek something that seems determined to remain unknown. How do you draw a map of a country that you cannot see? An entire continent that is shrouded in a permanent, impenetrable fog, its shores and mountains and rivers completely hidden from view. This is the profound and beautiful challenge that faces the scientists who search for dark matter. They are the modern-day equivalents of the ancient cartographers, tasked with charting the unknown, and they find themselves in a similar state of inspired frustration. The old maps of the world, the ones that were painstakingly drawn before the age of satellites and airplanes, had vast, empty spaces on them, often filled with drawings of mythical sea creatures and the stark warning, "Here be dragons." These were the honest acknowledgements of the limits of our knowledge. We are now in the process of trying to fill in the largest blank space on our map of the cosmos, and we must do so without being able to see the territory directly. Imagine one of those ancient cartographers on the deck of a small wooden ship, sailing along a coastline that is completely socked in by thick, grey fog. They cannot see the land itself, but they are not without clues. They can listen intently for the sound of waves crashing against a rocky shore, or the gentle lapping of water on a sandy beach. They can lower a weighted line into the water to measure the depth, noting where the seabed suddenly grows shallow. They can feel the direction of the wind as it is channeled through an unseen valley. From these indirect, sensory clues, these echoes and shadows, they begin to sketch a map. It is a map born of inference, a picture of the invisible coastline drawn from the way it affects the visible world. This is precisely the state of dark matter research today. We are the cartographers, standing on the deck of our small planet, peering into the cosmic fog. We cannot see the great, invisible continent of dark matter, but we can map its gravitational shores. We can listen to the way it makes stars move. We can measure how its unseen mass bends the light from distant galaxies, and we can see its fingerprints in the ancient light from the dawn of time. To turn these clues into a coherent map, we have turned to one of humanity's most powerful tools, the supercomputer. Inside these incredible machines, we create entire virtual universes. We begin by programming in the fundamental laws of physics as we know them, the rules of gravity and motion. Then, we add the ingredients. We start with the initial conditions of the very early universe, the recipe given to us by that baby picture of the cosmos, the cosmic microwave background, with all of its tiny, crucial ripples. We add the correct amount of ordinary matter, the stuff of stars and planets. And then, we add our theoretical recipe for dark matter. We tell the computer to assume that the universe is filled with a vast quantity of slow-moving, invisible particles that interact only through gravity. This recipe is known as cold dark matter, where cold simply means the particles were not moving at relativistic speeds in the early universe. Then, we press run, and the supercomputer begins to simulate 13.8 billion years of cosmic evolution. It is a process that can take months. A digital God game, where we see if our chosen ingredients and rules can bake a universe that looks like the one we live in. And in this, we have had a staggering, breathtaking success. The simulations that include cold dark matter are astonishingly good at reproducing the universe we observe. They spontaneously form virtual galaxies that spin and cluster in just the right way. They predict the pattern of gravitational lensing that we see through our telescopes. And most importantly, they create a cosmic structure on the largest of scales that is a near-perfect match for the real thing. We are drawing our map of the invisible, and when we hold it up to the faint glimpses of reality, we can see the coastlines match. This gives us enormous confidence that we are on the right track, that the fog is not hiding a dragon, but a real and solid continent. Yet, we must always remember the cartographer's humble wisdom. The map is not the territory. Science is not a perfect collection of absolute facts, but a continuous process of drawing and redrawing these maps, with each new observation, each new experiment, allowing us to sketch the coastline a little more accurately, to add a new feature, or to erase a mistake from a previous version. The beauty is not in having a finished, perfect map. The beauty is in the courageous and creative act of the attempt. And the maps our simulations are currently drawing for us reveal a breathtaking structure, a cosmic skeleton of staggering beauty and scale, upon which everything we have ever known is built. Imagine if the galaxies we see scattered across the night sky were not scattered randomly at all. Imagine they were not lonely islands of light floating in an endless, empty ocean of darkness. Imagine, instead, that they were like tiny, glittering dewdrops, clinging to the threads of a vast and utterly invisible spider's web that stretches across the entire universe. This is the astonishing picture that has emerged from our maps of the cosmos, the grand design that was sculpted by the unseen hand of dark matter. On the very largest of scales, the universe has a structure, a hidden architecture of profound and intricate beauty. It is a structure that connects everything, a single, vast, and coherent entity that we call the cosmic web. To truly feel the wonder of this, let us look to the world around us, for nature often repeats its most successful patterns on vastly different scales. Think of the forest floor, beneath the quiet cover of soil and fallen leaves. It is threaded through with a vast, hidden network of fungal threads, a mycelial web that connects the roots of individual trees to one another, sharing nutrients and information in a silent, subterranean conversation. A single organism can stretch for miles, a hidden network that is the true life of the forest. Or think of the 3 pounds of matter inside your own skull. It is made of billions of individual neurons, but their power comes from the way they are connected, the intricate, web-like network of axons and dendrites that creates a thought, a memory, or a dream. Nature, it seems, loves to build in webs. They are efficient, resilient, and they allow for complex connections. And the universe, it turns out, is no different. When we map the locations of hundreds of thousands of real galaxies in space, we see this pattern writ large upon the heavens. The galaxies are not distributed uniformly, like grains of sand scattered on a black sheet. Instead, they are arranged in enormous, thread-like structures called filaments, and in great, flattened walls. These glowing filaments of galaxies stretch for hundreds of millions of light-years, weaving their way through the cosmic dark. Where these filaments intersect, at the great cosmic crossroads, the gravitational pull is strongest, and we find the most massive objects in the universe. The great clusters of galaxies, each containing thousands of individual star systems. And surrounding these filaments and walls are the great cosmic voids, immense, almost empty bubbles of darkness, regions of space, hundreds of millions of light-years across, where very few galaxies are found. This is the cosmic web. Our supercomputer simulations have shown us, with startling clarity, that this beautiful structure could not have formed without dark matter. In the early universe, it was the gravity of the invisible dark matter that collapsed first, forming this great, underlying web-like structure. The ordinary matter, the familiar gas that would later form stars and galaxies, was then pulled by gravity onto this pre-existing dark matter scaffold. The visible universe, the one we can see with our telescopes, is just the luminous foam riding on the deep, dark waves of a much larger cosmic ocean. The galaxies are the bright lights that have turned on along the threads of the web, illuminating its structure for us. We do not live in an isolated galaxy. We live on one of the threads of this great web. Our own Milky Way is part of a small collection of galaxies called the Local Group, which itself is being pulled along a great filament towards the even larger Virgo cluster, which in turn is just one small part of the Laniakea supercluster, a single, glowing node in this unimaginably vast network. This idea fundamentally changes our perception of our place in the universe. We are not lost in an endless, meaningless void. We are part of a single, interconnected cosmic structure, bound together by a substance we cannot see. There is a hidden order, a hidden architecture, that connects our tiny home to the grandest structures in the cosmos. There is a gentle, persistent, gravitational pull that has guided the formation of everything we have ever known. And if we truly live within this great, dark web, does it affect our own galaxy, our own home, in ways we can feel, in ways we might even be able to detect, right here, right now? Right now, in this very moment, as you are lying here, listening to these words, something extraordinary is happening. Billions, perhaps even trillions, of invisible particles, ghosts from the dawn of time, are streaming silently through the room you are in. They are flowing through the roof, through the bed you are resting on, and through your own body, as effortlessly as a dream. They leave no trace, they make no sound, and they feel nothing. Yet this constant, silent, invisible river is real. It is the great mystery of the cosmos made immediate and intimate. It is the dark matter wind, and we are flying through it at this very second at an almost unimaginable speed. This is how the great cosmic web touches our daily lives, in a way so subtle and so profound that we have only just begun to comprehend its presence. To feel this on a more human scale, imagine standing on a quiet beach on a breezy day. You close your eyes. You cannot see the air, you cannot see the wind, but you have absolutely no doubt that it is there. You feel its constant, steady pressure against your face and your hands. You can hear it rustling in the dune grass behind you. You can feel its coolness on your skin. This constant, flowing presence is your direct, sensory evidence of the invisible ocean of air in which we live. And just as we move through our ocean of air, our entire solar system is moving through a much larger and more mysterious ocean of dark matter. Our galaxy, the Milky Way, is not just the beautiful, flat, spiral disk of stars that we see. The visible part of our galaxy is merely the bright center of a much, much larger structure. Our galaxy is embedded in the middle of a vast, roughly spherical cloud, a colossal halo of dark matter that extends far beyond the most distant stars. This halo is perhaps 10 times wider than the visible galaxy, and it contains the vast majority of our galaxy's mass. It is the unseen anchor, the gravitational foundation upon which our island of stars is built. And we are not stationary within this great, dark halo. Our Sun, along with all its planets, is hurtling through the galaxy in a grand orbit around the supermassive black hole at its center. We are moving at a staggering speed, approximately 220 kilometers per second, or nearly 500,000 miles per hour. As we race through the relatively static sea of dark matter particles that makes up the halo, we should experience a constant stream of these particles washing over the Earth, flowing through us from the direction in which we are traveling. This is the dark matter wind. It is an ever-present river of ghosts flowing through our world. And it is this wind that our deep underground detectors, those silent, patient jewels buried beneath mountains, are designed to feel. They are not just waiting for a random particle to wander by. They are oriented to feel the steady, directional flow of this galactic breeze. This idea leads to an even more beautiful and subtle prediction. While our solar system is orbiting the center of the galaxy, the Earth itself is also orbiting the Sun. For 6 months of the year, the Earth's motion is roughly in the same direction as the Sun's motion through the galaxy. During this time, we are moving faster through the dark matter halo, and the dark matter wind should feel slightly stronger. For the other 6 months, our orbital motion is against the Sun's motion, so we are moving more slowly through the halo, and the wind should feel slightly weaker. This should create a tiny, but predictable, annual variation in the number of dark matter particle interactions we detect. A slight increase and decrease in the signal that peaks in June and hits a low in December. This effect is called annual modulation, and it would be a powerful, smoking gun signature that what we are detecting is truly from the galactic halo. Some experiments have claimed to see hints of this signal, but the results remain controversial and unconfirmed by others. Still, the idea is profound. The greatest mystery in the cosmos is not something far away in a distant galaxy. Its presence is woven into the very fabric of our home. It is flowing through the ground beneath you and through the air around you. We are not just observers of the mystery. We are participants, swimming through it, breathing it, living within it at every moment. This constant flow, this invisible halo that holds our galaxy together, is more than just a passive presence. It has actively shaped the entire history and destiny of our Milky Way, and perhaps even the destiny of life itself. What does it take to build a galaxy that is fit for life? What are the necessary ingredients, the cosmic recipe, required to create a stable and nurturing home, a place where planets can form and life can have the billions of years it needs to emerge and evolve? We often think of the raw materials, the carbon, the oxygen, the water, but there is a more fundamental ingredient, a silent and invisible partner that made it all possible. Before you can have a flower, you must first have a garden. And in our universe, the dark matter was the patient, cosmic gardener that prepared the soil of the cosmos for us. Imagine a gardener in the early spring, preparing a patch of earth for planting. The soil is bare and thin. So, the gardener works the land, mixing in rich, dark compost and nutrients. They are creating a fertile and stable environment, a place that can anchor the roots of a small seed and provide the sustenance it needs to grow towards the sun. The rich soil itself will not become the flower. It will not unfurl the petals or create the beautiful colors. But without the foundation that the soil provides, the flower would never have the chance to exist at all. This is the role that dark matter has played in our cosmic story. It was not the seed of life, but it was the rich, dark soil that allowed the seeds of galaxies and stars to take root and flourish. In the early universe, after the Big Bang, the cosmos was filled with a nearly uniform and incredibly tenuous soup of hydrogen and helium gas. This was the raw material from which everything else had to be made. While this gas was spread almost perfectly evenly, there were those tiny, almost imperceptible clumps, those seeds that we saw in the cosmic microwave background. The problem was, the gravity of this ordinary matter alone was too weak, too feeble, to pull these wispy clouds together in any meaningful way. Left to its own devices, the primordial gas might have simply stayed as a thin, featureless fog as the universe expanded, never gathering into the dense pockets needed to ignite the first stars. But the gas was not alone. The universe was already filled with the invisible scaffolding of dark matter halos, which had been growing gravitationally since the very beginning. These halos were the patches of fertile soil, the pre-prepared gardens scattered throughout the cosmos. The ordinary gas, pulled by the immense gravity of these unseen structures, began to fall into the centers of these dark matter halos. It was here, in these protected gravitational wells, that the gas could finally become dense enough to collapse and form the very first generation of stars. These dark matter halos became the cosmic nurseries, the stable containers where galaxies could be built. Without the gravitational anchor of a dark matter halo, a young galaxy would likely be a chaotic and violent place, easily torn apart by interactions with other galaxies, its gas blown away before it could form long-lived stars. But nestled within their massive protective dark cocoons, galaxies like our own Milky Way could grow and evolve in relative peace for billions of years. This stability was the greatest gift of the galactic gardener. It allowed for not just one, but many generations of stars to be born, to live their lives, and to die. And it is this cycle of stellar life and death that created the very elements that we are made of. The hydrogen and helium from the Big Bang were not enough for life. Life needs heavier, more complex elements, like the carbon in our cells, the oxygen we breathe, and the iron in our blood. These elements are only forged in the fiery hearts of stars and in their explosive deaths. Generation after generation of stars, living and dying within the stable confines of the dark matter halo, slowly enrich the galaxy with these essential elements, seeding the interstellar clouds with the building blocks of planets and of people. We often think of ourselves as separate from the grand, impersonal workings of the cosmos. But the story of dark matter reveals a deep and intimate connection. Our existence is profoundly tied to this invisible substance that prepared the universe for us. It gathered the light, it nurtured the stars, and it created the calm, stable home where the intricate chemistry of life could find its footing. We are, in a very real and physical sense, the children of the dark. But not all cosmic interactions are so gentle and nurturing. The universe can also be a violent place. And so we must ask, what happens when these great, dark halos, these silent gardeners, collide with one another? Imagine two billowing clouds of smoke, one white and one grey, drifting towards each other on a perfectly still day. They meet, they merge, and for a moment they swirl together, but then they continue on their way, passing right through one another, each cloud emerging on the other side almost completely intact. Now, imagine taking two clay bullets and firing them at each other. When they meet in the air, they do not pass through one another. They collide in a sticky, messy impact, their momentum is halted, and they fall to the ground as a single, mangled lump. This simple distinction between things that can pass through each other and things that stick together is at the heart of the most stunningly powerful piece of evidence we have ever found for the existence of dark matter. It is a snapshot of a cosmic event of unimaginable violence, a photograph of two ghosts passing in the night, and it has been nicknamed, quite appropriately, the bullet cluster. To set the scene, picture a firework exploding high in the night sky. There is a brilliant flash and a beautiful, expanding sphere of hot, brightly coloured gas. But if you watch closely, you might also see the heavier, unexploded pieces of the firework, the dense pellets of burning magnesium, continuing to fly outwards on their original paths, quickly passing through and leaving the slowing cloud of gas behind. You see a natural separation of the components. The lightweight, interactive gas that collides with the air and slows down rapidly, and the heavy, dense projectiles that careen onwards, almost unaffected. This is precisely what we are seeing in the bullet cluster, but on a scale that is almost beyond human comprehension. What we call the bullet cluster is not a single object, but is in fact the scene of a cataclysmic collision between two entire clusters of galaxies. One, a smaller bullet cluster, has just recently passed directly through the center of a second, much larger cluster. They have passed through each other like two cosmic freight trains, and we are seeing the beautiful, messy, an incredibly informative aftermath of this collision, which happened about 150 million years ago. When we look at this scene with our telescopes, we can see three different things. First, using a normal optical telescope, we can see the galaxies themselves. Like the dense pellets in the firework, the individual galaxies are very small and dense compared to the vast distances between them. So, for the most part, they simply flew past each other during the collision without crashing, their paths altered only by gravity. Second, using an X-ray telescope, we can see the ordinary matter that exists between the galaxies. This is a colossal cloud of superheated gas. This gas makes up the vast majority of the normal visible matter in the clusters. And just like the two clay bullets, when these two immense gas clouds crashed into each other at millions of kilometers per hour, they did not pass through. They collided in a tremendous shockwave, slowing down dramatically and becoming even hotter, and this pile-up of hot gas now sits glowing brightly in X-rays right in the middle of the combined cluster. But then, we do the third and most crucial thing. We map the location of the mass in the cluster. We use the technique of gravitational lensing, looking at how the cluster as a whole bends the light from even more distant galaxies behind it, to trace the shape of its gravitational field. This tells us where the real substance, the real anchor of gravity, is located. And what we find is shocking and undeniable. Most of the mass is not in the middle with the hot glowing gas. Instead, the mass is located in two separate, distinct clumps, on either side of the wreckage. These clumps of mass have sailed right through the collision and emerged on the other side, completely unscathed and unslowed, leaving the sticky, normal matter behind in the middle. Just like the two clouds of smoke. This is the smoking gun for dark matter. The visible matter, the gas, has been physically separated from the invisible matter, the source of the gravity. The collision has torn them apart and shown us both in their separate locations. For a brief, illuminating moment, the ghost became visible. Not directly, but through its gravitational shadow. The universe pulled back the curtain for us, revealing the two fundamentally different realities that coexist in our cosmos. The sticky, interactive, light-filled world of ordinary matter that collides and clumps together, and the silent, aloof, non-interactive world of the dark, a substance that feels nothing but gravity and passes through everything, even a galactic collision of unimaginable force, as if it were not even there. This single observation provides such clear, unambiguous evidence for the existence of dark matter that it is almost impossible to explain away. And this makes it all the more baffling, all the more paradoxical, that our deepest, most sensitive, most carefully built traps here on Earth have remained so stubbornly and profoundly empty. This deepening paradox, this conflict between the clear cosmic evidence and the deafening terrestrial silence, forces us to pause and to ask a very difficult and very necessary question. Could we, despite everything, be wrong? What if there is no missing matter? What if there is no river of ghosts flowing through this room, no invisible halos holding the galaxies together, no new exotic particles to be found? What if, after all of this searching, the secret is not that the universe contains a mysterious, unseen substance, but that we have simply and profoundly misunderstood one of the forces we thought we knew best? What if the map of gravity that we have been using for over a century is, in some subtle way, incomplete? This is a dangerous and thrilling question. It is the kind of question that can feel like a form of heresy in science, a challenge to the very foundations of our understanding. And yet, it is the willingness to ask such questions that is the true engine of all scientific progress. To understand this perspective, imagine you have been given a beautiful, intricate, hand-drawn map of a great and ancient city. The map is a work of art, and for centuries, it has been perfectly reliable for navigating the city's streets. But now, as you try to use it, you find that it no longer works. You follow a street that the map says should lead to the main square, but instead, it leads to a dead end. You try to find a bridge that the map clearly shows, but it is no longer there. The map is not wrong about the old city. It is a perfect description of the city as it once was. But the city has grown and changed in ways the original mapmaker could never have foreseen. The map is no longer a complete description of the reality you are in. Some people, faced with this dilemma, might invent an explanation. They might say that there are invisible walls and secret passages that are forcing them off the map's path. Others might suggest a simpler, more radical solution, that it is time to draw a new map. This is the core idea behind a controversial but thought-provoking alternative to dark matter called MOND, which stands for Modified Newtonian Dynamics. This theory, first proposed in the 1980s by the physicist Mordechai Milgrom, suggests that we do not need to invent a new kind of matter to solve the mystery of the spinning galaxies. Instead, it proposes that we may need to slightly modify our law of gravity. The theory suggests that the laws of gravity laid down by Isaac Newton and Albert Einstein, while exquisitely perfect for the high-gravity environments of our solar system and for describing things like black holes, might work just a little bit differently in the incredibly low-gravity environments found at the edges of galaxies. MOND proposes that at very, very low accelerations, when the pull of gravity becomes incredibly weak, it does not fade away as quickly as we expect. It becomes slightly stronger, slightly more effective than our current theories predict. It is a subtle tweak, a small correction added to the equations, but its consequences are enormous. With this single modification, the problem of the impossibly fast spinning galaxies simply vanishes. The stars on the outer edges are moving so fast because, in that low acceleration environment, the grip of gravity is just a little bit stronger than we thought, precisely the right amount stronger to hold them in their orbits without the need for any dark matter at all. MOND is remarkably successful at predicting the rotation speeds of a huge variety of galaxies, often more accurately than the dark matter models. It is a powerful and elegant idea. However, it is a minority view for a reason. While it works beautifully on the scale of individual galaxies, it has struggled mightily to explain the universe on larger scales. MOND has a very difficult time accounting for the evidence we see in the collision of the bullet cluster, where the gravity is clearly separated from the visible matter, and it struggles to provide a natural explanation for the formation of the cosmic web, the very structure that dark matter seems to explain so perfectly. Nevertheless, the existence of this idea teaches us something beautiful and essential about the self-correcting nature of science. It is not a rigid set of beliefs, but a dynamic and open-ended process of inquiry. It allows for, and in fact requires, these heretical ideas to challenge the mainstream consensus. The debate forces everyone to re-examine their assumptions and to look at the evidence more critically. It asks us to confront a philosophical choice. Which is the more elegant and believable explanation? Is it easier to believe in a vast, invisible universe of a completely new kind of substance that we have never, ever detected directly? Or is it easier to believe that a fundamental law of nature, one that we hold almost sacred, might be just a little bit incomplete? While MOND has its challenges, and the vast majority of the evidence still points towards the reality of dark matter, the conversation continues. And this very sturdiness of the dark matter theory, its ability to withstand these challenges, leads us to an even deeper and more philosophical puzzle about its nature. Why is there not more dark matter? And why is there not less? This is not a frivolous question. In fact, it is one of the deepest and most nagging puzzles in all of cosmology, a question that hints that we may be on the verge of uncovering a new and profound principle about how our universe works. We have spent so much time contemplating the very existence of dark matter that we rarely stop to consider its specific abundance, the simple fact of how much of it there is. And when we do, we find something that looks suspiciously like a clue, a strange and unlikely cosmic coincidence that may be the key to unlocking the entire mystery. The universe, it seems, may be trying to tell us something in the simple ratio of the seen to the unseen. To feel the strangeness of this, imagine two people walking through a vast, ancient forest. They begin their journeys at completely different starting points, miles apart from one another. They are walking at different speeds and in different directions, each on their own separate path. And yet, for one brief, fleeting moment, in a small, sun-dappled clearing, their paths intersect. They nod to each other in passing and continue on their way. An outside observer, watching this happen, would be struck by the beautiful unlikeliness of it. There was no reason for their paths to cross. The forest is immense, and their journeys were independent. The fact that they met at all, in that one specific place, at that one specific time, feels like it must mean something. It feels like more than just a random accident. It feels like a hint of some hidden connection, some underlying story that brought them together. Physicists feel much the same way when they look at the amounts of ordinary matter and dark matter in our universe. When we measure the cosmic ingredients, as we have done with incredible precision by studying the cosmic microwave background and the large-scale structure of the universe, we find a curious relationship. For every 1 kilogram of the familiar, visible matter that makes up stars and planets and people, the universe contains roughly 5.3 kilograms of dark matter. The ratio is about 5 to 1. Now, on the surface, that might not seem particularly special, but to a physicist, it is utterly baffling. These two substances, ordinary matter and dark matter, are thought to be completely different things. They were likely born from different processes in the ultra-hot chaos of the Big Bang. They interact via different forces. They live in essentially separate worlds. There is no obvious, fundamental reason why the amount of one should have anything at all to do with the amount of the other. It would be far less surprising if the ratio were 1,000,000 to 1 or 1,000,000,000 to 1, with one substance being just a tiny trace contaminant of the other. But instead, their energy densities are, cosmologically speaking, in the same ballpark. Their paths have crossed in the cosmic forest. This coincidence has given rise to what many call the WIMP miracle. It is not a miracle in a supernatural sense, but in the sense of a beautiful and unexpected alignment between theory and observation. It turns out that when particle physicists build theories that contain new, heavy, weakly interacting particles, the very definition of a WIMP, and they calculate how many of these particles should have been created and how many should have survived the intense heat of the Big Bang, they arrive at a predicted abundance. And that prediction, arising from completely independent theories about particle interactions, just happens to be almost exactly the amount of dark matter we actually observe in the universe. This is a stunning result. It is as if we guessed the weight of a stranger just by looking at the color of their eyes. It suggests that the WIMP idea is not just a wild guess, but is rooted in a deep and potentially correct understanding of physics, hinting at a hidden connection, a hidden symmetry between the visible world and the dark. Is this cosmic composition a random, meaningless accident? Or does it point to a deeper, underlying principle of balance, a law of nature that we have not yet uncovered? The numbers seem too neat, too suggestive, to be a mere coincidence. It feels like a message left for us in the bookkeeping of the cosmos, telling us that the dark world and our world are more intimately related than we ever thought possible. And perhaps this hidden symmetry is trying to tell us something even more profound. Perhaps it is a clue that dark matter is not just a single, lonely particle, but that its world is just as rich and just as complex as our own. What if the dark matter in the universe has its own version of light? What if it has its own rich and complex chemistry, its own set of fundamental forces, its own private conversations that have been happening all around us, completely unheard, for 13 billion years? We have spent our journey so far imagining dark matter as a simple, solitary, and silent substance. We have pictured it as a single species of ghost particle, aloof and non-interactive. But the universe is rarely so simple, and one of the most exciting and mind-expanding frontiers in theoretical physics today is the idea that dark matter is not simple at all. It may not be a single particle, but an entire, parallel world of particles, a shadow cosmos with its own laws of physics, a place that has been nicknamed the dark sector. To grasp the beautiful and dizzying implications of this, imagine yourself in an airplane at night, flying high above a vast and sprawling city. You look down out of the small window. You cannot hear the sounds of the traffic. You cannot smell the food from the thousands of restaurants. You cannot feel the energy and the life of the millions of people down below. All you can see is a beautiful, intricate pattern of lights. You see the bright, glowing arteries of the highways, the dense clusters of light that mark the city centre, the dimmer, warmer glow of the suburban neighbourhoods. You can tell, just from observing these patterns of light, that the city is a complex and vibrant place. You can map its structure, you can see how it is organised, but you have absolutely no access to the rich, complex, sensory world of the city itself. You are an outside observer, able to see only the city's broadest, simplest structure, while being completely blind to the intricate life unfolding within it. This is the relationship we may have with dark matter. We can see its lights, its broad gravitational structure that holds galaxies together and forms the cosmic web. But we may be completely blind to the possibility that it has its own rich, internal life. This is the central idea of the dark sector. The theory proposes that our standard model of particles, the cast of characters that makes up our visible world, is not the only cast in the cosmic play. There may be a second, parallel set of particles, the particles of the dark sector. This sector could have its own version of the electron, its own version of the quark, and most importantly, it could have its own set of forces. Perhaps there is a dark photon, a particle that carries a form of dark light or dark electromagnetism. This dark photon would be completely invisible to us, and our photons would be completely invisible to it. But to the particles of the dark sector, it would be as real as the light from the sun. If this were true, then dark matter could be astonishingly complex. Dark matter particles could exchange dark photons, allowing them to interact with each other, to repel each other, to bind together. They could form dark atoms, with a dark nucleus and a dark electron orbiting it. These dark atoms could then combine to form dark molecules, engaging in a rich and complex dark chemistry. This would immediately explain why it has been so impossible to detect dark matter in our laboratories on Earth. Our experiments are all built to interact with particles from our world. They are designed to see a flash of our light, or feel a push from our electromagnetic force. Trying to detect a dark matter particle with such a device would be like trying to listen to a radio station with a telephone. We are simply using the wrong tools, built for the wrong reality. This idea opens up a universe of possibilities. Could dark matter form its own structures, its own dark planets, or even dark stars, powered by dark forces and shining in dark light, completely invisible to our telescopes? It is a deeply speculative, but thrilling, possibility. The universe might be twice as rich, twice as complex, and twice as beautiful as we have ever imagined. There could be an entire shadow cosmos, living alongside ours, a silent and intricate partner in the cosmic dance, its presence revealed to us only by the gentle, persistent tug of its gravity. The existence of such a rich, hidden world would fundamentally change our understanding of reality, and it would also have profound implications for the grand, overarching story of the cosmos and the ultimate fate of everything. Does the universe end in a blaze of glory, or does it fade into a whisper of ice? This is the ultimate question of cosmology, a question that extends our gaze to the farthest conceivable shores of time. For millennia, we have wondered about the end of the world, but now we can ask about the end of everything, the final chapter in the story of space and time itself. And the answer, it seems, is held in the delicate and unseen balance of the two greatest mysteries in the cosmos. The fate of all existence is a grand cosmic battle, a slow and silent tug of war, being fought between the two dominant, invisible components of our universe. On one side, there is dark matter, the great gatherer, and on the other, there is its even more mysterious cousin, dark energy. To imagine the end, picture a slow, gentle snowfall on a quiet winter's night. You are warm inside, looking out the window as the first flakes begin to drift down, each one a perfect and unique crystal. As the hours pass, the snowfall becomes steadier, and a soft, white blanket begins to cover everything. It covers the dark branches of the trees, the sharp angles of the rooftops, and the cold, hard lines of the street. The world becomes quiet, muffled, and serene. All the distinct details of the landscape are slowly erased, smoothed over into a single, uniform, and peaceful expanse of white. This feeling of a slow, gentle, and inevitable fading, a peaceful descent into a state of perfect uniformity and stillness, is perhaps the closest we can come to imagining the likely ultimate fate of our universe. The story of this fate begins with the two dark titans. We have come to know dark matter as the universe's great sculptor and anchor. Through its immense gravitational pull, it gathers matter together, it builds the galaxies, and it holds them in its steady embrace. On a cosmic scale, The gravity of all the dark matter and all the ordinary matter in the universe is constantly acting as a cosmic brake, pulling inwards, trying to slow down the expansion of the universe that began with the Big Bang. For a long time, we thought this was the only force at play, and the only question was whether there was enough matter to eventually halt the expansion and pull everything back together. But in the late 1990s, we discovered something shocking. The expansion of the universe is not slowing down at all. It is accelerating. It is speeding up. There must be another, even more mysterious force at work, a force that is pushing the universe apart. This force was given the name dark energy. We do not know what it is, but it seems to be a property of space itself, a kind of anti-gravity that causes the fabric of the cosmos to constantly stretch and expand at an ever-increasing rate. And so, the ultimate fate of everything is a competition between these two opposing forces. It is a battle between the inward pull of dark matter's gravity and the outward push of dark energy's expansion. If dark matter's gravity were to somehow win, the universe might one day slow its expansion, stop, and then reverse, collapsing back in on itself in a fiery and spectacular big crunch, a kind of Big Bang in reverse. But all of our current evidence suggests that dark energy has the upper hand. Its gentle, persistent push is overpowering gravity's pull. If this continues, as it seems it will, then the universe is destined for a very different kind of end. Galaxies will continue to fly away from each other, faster and faster. Distant galaxies will eventually be moving away from us so fast that their light can no longer reach us, and they will disappear from our sky, one by one, leaving our own local group of galaxies as a lonely island in an endless, empty void. Within this island, the stars will slowly burn through their fuel and die out. The universe will grow colder, darker, and emptier. Eventually, even the black holes themselves may evaporate into nothingness, leaving behind only a diffuse, cold, and uniform sea of elementary particles. This is the heat death, or the big freeze. A slow, quiet, and peaceful fading into an eternal twilight. Our lives are finite, and so too, it seems, is the universe, with its own grand story of a fiery birth, a vibrant life, and an eventual, quiet end. There is a strange and sublime comfort in this cosmic-scale melancholy, and the story is made all the more poignant, all the more profound, by the fact that the main characters who are deciding this ultimate fate, both dark matter and dark energy, are completely invisible to us. And so, as we peer into this distant, cold future, what is the next step for us? The brief, conscious observers of this grand and silent drama. Have you ever heard the old story of the person who is searching for their lost keys on a dark street at night? A police officer comes by and sees them on their hands and knees, carefully scouring a small, round patch of ground directly beneath a bright, solitary street lamp. The officer, wanting to help, asks, "Is this where you lost your keys?" The person looks up and replies, "No, I think I lost them over there, in the dark part of the park." The officer is confused. "Then why," he asks, "are you looking for them here?" The person replies with a simple and profoundly human logic. Because this is where the light is. This simple story, often told as a joke, is one of the most powerful and important analogies for the philosophy of science, and it perfectly captures a deep and difficult question we must ask ourselves about our long and so far fruitless search for dark matter. Let us linger on that image for a moment. Picture the scene: an entire city park, shrouded in a deep and profound darkness. There are trees and benches and paths, all hidden in the blackness of the night. But in the middle of it all is a single, tall lamppost, casting a perfect, bright circle of light onto the pavement below. Inside this circle, every crack in the concrete, every fallen leaf, is visible in sharp, clear detail. Outside the circle, there is only impenetrable shadow. The person searching for their keys is not being irrational. They are being practical. It is impossible to search the entire, dark park. The only place where a search is even possible, the only place where you have a chance to see the keys if they happen to be there, is within that small, illuminated circle. And so, this is where we look. we look where the light is. In our quest for dark matter, the lamppost is our current, established understanding of physics. It is the standard model of particles and forces, a theory of breathtaking success that has illuminated so much of the world for us. And within the bright light of this theory, there are certain logical places to look for answers to the universe's remaining mysteries. The idea of the WIMP, the weakly interacting massive particle, is a perfect example. It arises naturally from some of our leading theories that try to extend the standard model. Our theories predict that such a particle should exist. In essence, our beautiful theories of physics are shining a bright light on a very specific spot on the ground and telling us, the keys are probably right here. And so, we have, quite logically, built our immense, deep, underground detectors, our vats of liquid xenon, and our crystals of pure germanium, as perfect tools to search within that specific circle of light. We have spent decades on our hands and knees, carefully scouring the ground beneath the WIMP lamppost, because that is where our theories told us we had the best chance of finding something. But after all this time, the keys are not there. The ground beneath the lamppost is empty. And so, we are faced with the most difficult of questions. Do we simply need a brighter lamppost, a more sensitive detector that can see even smaller, fainter keys within the same circle of light? Or is it possible that the keys were never here to begin with? Is it possible that the true nature of dark matter is something completely unexpected, something that lies far out in the darkness, in a place where the light of our current theories does not reach? Perhaps dark matter is not a WIMP, or an axion, or a primordial black hole, but something so strange and new that we do not yet even have the language or the mathematics to describe it. This is the great and humbling challenge of searching for the truly unknown. The search for dark matter is therefore not just a search for a new particle. It is a search for the limits of our own knowledge, a profound lesson in intellectual humility. It teaches us that the map is not the territory, that the theories we hold dear are not reality itself, but just our best attempt to draw a circle of light in an overwhelmingly dark and mysterious world. The silence from our detectors is not a failure. It is a quiet and persistent invitation to be more creative, to be more courageous, and to find new ways to cast a little more light into the darkness. And perhaps the greatest discoveries of the future will not come from building ever bigger and more powerful machines to search under the same old lamppost, but from a different way of thinking, a final, inward turn. What is the most profound and intractable mystery you can possibly contemplate? For many of us, after this long journey through the cosmos, the answer might seem to be the nature of dark matter. But there is another, perhaps even deeper mystery, one that is not found in the vast, cold distances between the stars, but in the warm, quiet, and intricate universe that exists behind our own eyes. As our search for answers in the outer world leads us to a place of profound silence and humility, it may be time for a final, inward turn. For it is possible that the structure of the cosmic mystery, its very shape and character, is a perfect reflection of the mystery of ourselves. The two great dark problems, of the cosmos and of consciousness, may in fact be one and the same. To begin this final step of our journey, take a moment to observe the nature of a single thought. Try to notice where it comes from. One moment, there is nothing, and the next, an idea, a memory, a worry, or a feeling simply appears, fully formed, in the landscape of your awareness. It seems to have emerged out of a silent emptiness. We can, with the tools of modern science, watch this process from the outside. We can place a person in a brain scanner and see the intricate, electrical storm of their neurons firing. We can map the flow of blood and the exchange of chemicals. We can pinpoint the exact physical, biological processes that correspond to the act of thinking. We can describe the machinery of the brain in exquisite detail. And yet, after all of that, we are no closer to explaining how that physical process, that pattern of electricity and chemistry, becomes the subjective, private, inner feeling of having an idea, or of seeing the color red, or of feeling a sense of love. A subjective experience emerges from an objective, physical machine, and the chasm between the two is absolute. This is what is often called the hard problem of consciousness, and its shape is identical to the dark matter problem. In cosmology, we face an explanatory gap. We can see and measure with incredible precision the effects of dark matter. We see its gravitational pull on stars. We see the way it bends light. We see its imprint on the entire structure of the universe. We have a complete description of what it does, but we have no idea what it is. We cannot seem to cross the gap from its external effects to its internal nature. In neuroscience, we face the very same explanatory gap. We can see and measure the effects of consciousness. We see the neural firings, the brain waves, the complex behaviors it produces. We have an increasingly complete description of what the brain does, but we have no idea how that activity becomes the subjective experience of what it is to be you. Both are dark problems. Both involve a reality that is not directly observable from the outside, but whose effects on the world are powerful and undeniable. Both profoundly challenge the simple idea that what you see is all there is. The universe is not only stranger than we imagine, it is, as the scientist J.B. S. Haldane once said, stranger than we can imagine. And our inability to solve these two great mysteries might be a gentle hint that our current methods of inquiry, our lamppost of looking only for objective, external, third-person answers, may be incomplete. Perhaps a full understanding of reality will require us to find a new science, a new way of thinking that can build a bridge between the outer world of matter and the inner world of experience. Perhaps consciousness is not something that happens only in brains, but is a fundamental property of the universe, just like gravity or space-time. We do not know. But the parallel is a lesson in humility. It reminds us that the tools we use to probe the great outer darkness, curiosity, a comfort with uncertainty, pattern recognition, and the courage to embrace a profound mystery without demanding a simple answer, are the very same tools we need to probe our own inner darkness. The quest to know the universe and the quest to know ourselves are, in the end, the same beautiful, open-ended journey. And so we find ourselves at the end of our exploration, back in the quiet of the night, looking up at the very same stars where we began our story. We began our journey with a simple question, born from the sight of a spinning galaxy. Why is the universe not flying apart? And now, after traveling across billions of light years and billions of years of cosmic time, after descending into the deepest minds on Earth and soaring into the most speculative realms of human thought, we find that the simple, honest answer is that we still do not know. The great and beautiful question remains. And perhaps that, in the end, is the most wonderful and important part of this entire story. The destination of our journey is not an answer, but a deeper and more profound appreciation for the mystery itself. Imagine, for this one last moment, that you are sitting on the shore of a perfectly calm and silent lake, late at night. The air is still, and the dark water is a perfect mirror, reflecting the uncountable stars of the Milky Way above. You can see the sweep of the galactic plane, the dark dust lanes, the faint, shimmering glow of distant nebulae, all of it doubled in the water before you. You do not need to know the name of every single star, or its distance, or its temperature, to be filled with a sense of awe and profound peace. The sheer, overwhelming beauty of the scene is not diminished by your lack of complete knowledge. In fact, it is enhanced by it. The mystery is a part of the magic. The feeling of being a small, conscious part of something so vast and so enigmatic is not a source of fear, but a source of the deepest and most gentle wonder. This is the place where our search for dark matter has led us. It has led us back to the shore of the cosmic ocean, not with a complete map, but with a newfound appreciation for its infinite and beautiful depths. We began our story with the quiet courage of Vera Rubin, who trusted her observations over her textbooks and revealed that the cosmic carousel was spinning impossibly fast. We learned that this was not a small error, but the sign of a vast, unseen anchor of gravity, an invisible substance that outweighs all the stars we can see by more than 5 to 1. We followed its gravitational shadow across the cosmos, watching it bend and magnify the light from the most ancient galaxies, revealing its presence in the very fabric of space-time. We listened for its echo from the dawn of time, finding its fingerprints in the baby picture of the universe, and realizing that it was the silent architect, the cosmic gardener, that built the great web of galaxies and nurtured our own home so that life could one day emerge. We explored the fantastical menagerie of candidates for what it could be. The shy, heavy wimps, the whispering, wave-like axions, and the ancient, haunting, primordial phantoms. We journeyed deep underground to the quietest places on Earth, where humanity has built its most sensitive traps to try and catch a single one of these ghosts. And we have shared in the profound silence of those empty detectors. We have wrestled with the heretic's question of whether we might have misunderstood gravity itself, and we have marveled at the cosmic coincidence that hints at a deep connection between our world and the dark. And now, here at the end, we are left not with a solution, but with a gift. The search for dark matter teaches us a final, gentle, and essential lesson. It teaches us to find comfort in mystery. It shows us that the universe is not a simple puzzle to be solved and then put away on a shelf, but a grand and unfolding story to be experienced, to be participated in. The darkness in the cosmos is not an absence of light, but a presence of the unknown. And the unknown is the engine of our curiosity, the source of our humility, and the reason we will always continue to look up at the night sky, filled with a quiet and hopeful wonder. Thank you so much for joining me on this long and gentle journey. I hope it has brought you some measure of peace, rest, and perhaps a little bit of cosmic perspective. If you have any thoughts or feelings you would like to share, I would be so happy to read them in the comments below. And if you have enjoyed our time together, please consider liking and subscribing so that we may continue to explore these quiet mysteries together. Wherever you are, I wish you a very deep and peaceful sleep, filled with the most wonderful dreams. Good night.